Alright guys, today we're going to take a look at some examples regarding what we call the combined gas law. So we've talked about a few laws. We talked about Dalton's law, Boyle's law, and Charles' law. So today we're going to look at the combined law. Let me zoom in a little bit here. So the combined law includes, and you can see in the equation, pressure, volume, and temperature. So you're comparing pressure, volume, and temperature of a particular gas before, or the original pressure, volume, temperatures. You're comparing those to the new pressure, volume, and temperature. So everything here that's labeled on the left as a P1, V1, or T1, these are all original values or starting values. So P1 is the starting pressure or the original pressure. V1 is the original volume, and T1 is the original temperature. So everything on the right with a P2 or 2 as a subscript, these are the new values. So these are the new pressure, volume, and temperature. Okay. So I'll show you how to do some calculations related to the combined law. One thing that I want everyone to remember is that, and add a couple notes here, temperature must be in Kelvin. Okay, so in case you have forgotten, to convert to temperature in Kelvin, you're going to take your temperature in Celsius and you're simply going to add 273 degrees to it. One other note that I want you to add is that your pressure units must be the same. So your units for pressure must be the same. Okay, so a couple other things I want to remind you before we get going. Is your conversion factors. So remember that, actually before we get to conversion factors, remember standard temperature and pressure, STP, is 0 degrees Celsius and 1 atmosphere. Okay, so 1 atmosphere is equal to 760 millimeters of mercury, and which is equal to 101.3 kilopascals. So standard pressure is 1 atmosphere. But what if your problem doesn't have a measurement in atmospheres? Well, know that 1 atmosphere equals 760 millimeters of mercury. So this is also standard pressure. 1 atmosphere is equal to 101.3 kilopascals. So this is also standard pressure. 0 degrees Celsius. Remember, all temperatures must be in Kelvin. So if I add 273 to that, then my standard temperature in Kelvin is 273 Kelvin. Okay, so just some things to keep in mind as we go through these examples. All right, so number 1 says a filled balloon has a volume of 50 liters at 25 degrees Celsius and standard pressure. What volume will it have at 0.855 atmospheres and 10 degrees Celsius? Okay, so what I want you to get in the habit of, and this is easy because all of these examples are combined gas laws, I want you to practice writing your variables all on one side before you get started. So our pressure, our volume, our temperature originally, and then our new pressure, our new volume, and our new temperature. Okay, so now we can go through and read the problem and fill in the variables that are provided. So a filled balloon has a volume of 50 liters at 25 degrees Celsius. So this is implying that this is your starting volume. Liters measures volume, so this is V1. 25 degrees Celsius. That's the temperature at which the balloon is at currently. So that's my T1. So I'll go ahead and fill those in. So volume is 50 liters. Temperature is 25 degrees Celsius. And standard pressure. Okay, well, standard pressure is normally in atmospheres, but it can also be millimeters of mercury or kilopascals. So if you continue reading, you'll notice that it says, what volume will it have at 0.855 atmospheres? So I know that my unit of pressure is in atmospheres. Remember that my units for pressure have to be the same. So if the new pressure is in atmospheres, that means my starting standard pressure must be also in atmospheres. So standard pressure in atmospheres is 1. Okay. So what volume will it have? So that means I need to solve for a new volume at 0.855 atmospheres. So this is my new pressure. So 0.855. And the temperature is 10 degrees Celsius. Okay. So before we can begin, remember that our temperature must be in Kelvin. So for each temperature in Celsius, you must add 273. So 25 plus 273 gives you 298 Kelvin. And 10 degrees Celsius plus 273 gives you 283 Kelvin. Okay. So our equation says P1 V1 over T1 equals P2 times V2 over T2. So now we just substitute everything that we know. So my P1, my original pressure, is 1 atmosphere. My original volume is 50 liters. My original temperature is in Kelvin 298. Equals my new pressure is 0.855. My new volume is unknown, so I'm going to leave it as V2. And my new temperature is 283 Kelvin. So now we've got all our variables substituted into my equation. Now I proceed to solve. So I've got a fraction on the right, a fraction on the left, which means that I'm going to cross multiply in order to get V2 by itself. So the first thing I'm going to do is I'm going to cross this right here. So 1 times 50 times 283. So 1 times 50 times 283 gives me 14,150. Okay, now I'm going to cross 298 times everything in the numerator on the other side. So 298 times 0.855 times V2. Well, I don't know the value of V2, so it's going to stay a V2, so I'm really just multiplying 298 times 0.855. So when I multiply those two together, I get 254.79. And like I said, we don't know the value of V2 yet, so I'm going to leave it as V2. So now, in order to get V2 by itself, I've got to divide both sides by 254.79. So on one side, I got 14,150 divided by 254.79 equals V2. And when you divide that, your value for V2 becomes 55.54 liters is your new volume. All right, let's go ahead and look up at the next example here. I've got a 700 milliliter gas sample at STP is compressed to a volume of 200 milliliters and the temperature is increased to 30 degrees Celsius. What is the new pressure of the gas? Okay, so again, we know this is the combined law, so let's go ahead and write our variables on the left. So I've got P1, V1, T1, P2, V2, and T2. So P1, V1, T1 are starting pressure, volume, and temperature. P2, V2, and T2 is our new pressure, volume, and temperature. All right, so I've got a 700 milliliter gas sample. So this is implying that this is what you're starting with. So 700 milliliters. It's at STP, standard temperature and pressure. All right, so standard temperature and pressure. Standard temperature is 0 degrees Celsius. Standard pressure is 1 atmosphere. I'm going with atmospheres because I don't know what the new pressure is. Essentially, this pressure could be anything as long as your new pressure is in the same unit. So I'm just going to go with atmospheres. It's going to make the calculation a little bit easier. So let's keep reading. It's compressed to a volume of 200 milliliters. So it was 700, now it's 200. So this is my new volume. And the temperature is increased to 30 degrees. So it was 0 at standard temperature. Now it's 30 degrees. So my T2 is 30 degrees Celsius. I want to figure out the new pressure. So I'm solving for P2. So remember, before we start, our temperature must be in Kelvin. So for each degree Celsius, I'm going to add 273. So 0 plus 273 is 273. And 30 plus 273 is 303. And these are both in Kelvin. So now I can get started. So P1 V1 over T1 equals P2 times V2 over T2. All right, so my original pressure is 1. My starting volume is 700. My original temperature is in Kelvin, 273. Equals my new pressure is unknown. My new volume is now 200. And my new temperature increased to 30 degrees, which is 303 Kelvin. So now we are going to cross multiply. So I'm going to cross this part first. So 1 times 700 is 700. So 700 times 303 is going to give you 212,100. So 212,100 equals, and then 273 times everything in the numerator. So we don't know the value of P2 yet, so I'm just going to multiply 273 times 200. And that gives me a value of 54,600. And multiplied by P2. So now to get P2 by itself, I've got to divide over 54,600. So I get 212,100 divided by 54,600 gives me my new pressure. So when I type this into the calculator, I get a value of 3.88, and my units for pressure were in atmospheres. Again, this unit doesn't really matter much as long as both of these units are the same. So I could have gone with 760 millimeters of mercury here, which means my answer would have also been in millimeters of mercury. But I went with ATM because it's easier to multiply by 1 than 760. All right, so 3.88 atmospheres is my new pressure. Let's try example number 3. Sample of ammonia gas occupies a volume of 1.58 liters at 22 degrees Celsius and a pressure of 0.983 atmospheres. What volume will the sample occupy at STP? So again, I've got pressure, volume, and temperature. This is the combined law. So I'm going to list my variables. P1, give me 1 second. P1, V1, T1 is my original pressure, volume, temperature, and then P2, V2, T2 is my new pressure, volume, and temperature. So the sample of ammonia gas occupies a volume at 1.58 liters. So it's telling you that the volume is 1.58 liters. And it's at 22 degrees Celsius. So that is my starting temperature. And a pressure of 0.983 atmospheres. So that's my starting pressure. So 0.983 atmospheres. What volume will the sample occupy? So it's telling you it wants to know the new volume at STP, standard temperature and pressure. All right, so standard temperature, 0 degrees Celsius. Standard pressure, well, if the starting pressure here is in atmospheres, this has to also be in atmospheres. So that means my new pressure is 1 atmosphere. That's standard pressure. All right, so I'm solving for the new volume. P1 times V1 over T1 equals P2 times V2 over T2. So now we'll plug in our values. So for P1, my original pressure, I had 0.983. My original volume was 1.58. And my starting temperature was 22 degrees Celsius. Now, I almost forgot, we've got to convert these to Kelvin. So 22 plus 273 gives you 295. And 0 plus 273 is 273. All right, so now we can plug in T1 is 295. Equals my new pressure is 1 atmosphere, the new volume is unknown, and the new temperature is 273. All right, so now we are going to do cross multiply. So everything on the top here, 0.983 times 1.58, cross multiplied with 273, gives me a value of 424.007. And then 295 times 1 times V2. I don't know the value of V2, but I do know what 295 times 1 is. So 295, and then still multiplied by V2. The last step, move 295 to the other side by dividing. So your value for V2 becomes 1.44 liters. All right, and our last one here. The volume of a balloon is changed to 2.37 liters at a temperature of 19 degrees Celsius and a pressure of 99.7 kilopascals. What was the pressure of the balloon when its values were 2.42 liters of helium at a temperature of 27 degrees Celsius? So pressure, volume, and temperature, the combined law, so P1, V1, T1 equals P2, V2, T2. Okay, so this says the volume of a balloon has changed to, which means it was something else originally. The next sentence says, what was the pressure of the balloon when its values were 2.42 liters at a temperature of 27 degrees? So it's implying that second sentence that those values were the starting values. So the starting volume is 2.42. The starting temperature is 27. And we want to figure out the starting pressure. The new volume is 2.37 liters, and the new temperature is 19 degrees Celsius, and the pressure was 99.7 kilopascals, kPa. Now, we set this up to solve for the starting pressure. If you had put it in opposite order, thinking that maybe P2, V2, and T2, 99.7, 2.37, and 19 were original values, and you're solving for the new pressure, it wouldn't make any difference. You would still get the same calculation. So my equation says, actually I almost forgot again, I've got to convert my temperatures to Kelvin. So 27 degrees plus 273 gives me 300 Kelvin. And 19 degrees plus 273 gives me 292 Kelvin. Now we can start. So P1 V1 over T1 equals P2 V2 over T2. So my starting pressure is unknown. My starting volume is 2.42. And my starting temperature in Kelvin is 300. My new pressure is 99.7. My new volume is 2.37. And my new temperature is 292 Kelvin. So cross multiply. 99.7 times 2.37 times 300 gives you 70,886.7. And then everything on the numerator multiplied by the denominator on the other side. We don't know the value of P1 yet, but we can multiply 2.42 times 292. And that gives us a value of 706.64 times my starting pressure. So now to get pressure by itself, I'm going to divide 70.886.7 divided by 706.64 is going to give me my starting pressure. And my starting pressure after I divide. This is a comma, by the way, 70,000, is 100.32 kPa, kilopascals, as my starting pressure. So hopefully you can use these 4 examples to help you with the classwork. If you have any questions, either send me an email or join me for tutoring on Thursday.